Hey guys, today I want to talk about something called Ralph Wiggum. But today I want to talk about why it's actually not enough. Not enough. And it's a little bit shocking that it's making so many rounds on social media despite the fact that it's actually a little bit of a naive solution, right? It's loop an LM forever, right? Ask it to do a task. And it will gracefully exit when your tokens run out for your subscription and then continue to try to finish the task until it's done. And it will just continue over and over and over and over. Well, that is actually quite a naive solution. I think a lot of people are starting to find this out as they're trying to produce actual software. And the question is, enough for what specifically? So what we mean here is, obviously you want quality code. At minimum, you want working code. And as a lot of people are starting to find out as they're using Ralph Wiggum, this is often not the case, except for maybe the most trivial problems. And that is because of something called LM drift. So what is LM drift? Well, this is when an LM deviates from its original instructions to start to hallucinate or make up information. And that is because of two different things, right? It's because of something called context loss. And this is when an LM starts to lose memory of what it was even doing to begin with, because over time, the LM only has a limited window for memory, right, called the context window. And this needs to get filled up with new things such as new requests, new information, tool calls to maybe call like, a SQL database or something like that. And as it does that, it needs to compact the memory so that it can fit this new information in. And so it'll eventually lose the old information because compression is not lossless, right? You can only fit so much information in so much space. The other thing that causes LM drift is called graceful degradation. And graceful degradation is a fancy term for essentially the LLM starts to gracefully lower the quality of its output because it's not able to find the information for the actual answer. So it will try to approximate the closest answer. And so it will come up with as many backup plans as possible, right? As many backup plans as possible. And then eventually it will come to a point where it runs out of backups as possible solutions. And then it will just make one up, right? It will hallucinate. It will lie to you, which is obviously not good. When you're developing software, you don't want the LM to lie to you, and you don't want it to produce broken code, right? Because that's usually what it ends up being. It's just broken code that's just made up out of thin air, code that won't actually run. Or if it does run, it runs in a way that is not intended, right? It's broken, it does things that are dangerous, etc. So real quickly, let's get back to first principles here. What is the selling point of Ralph Wiggum? The selling point of Ralph Wiggum is that it's autonomous. And the idea of autonomous is that it runs on its own, right? But I think what people really mean by autonomous is it's able to do things on its own. And that's what I would call truly autonomous. Now, what we end up realizing when we look very deeply into this is that the gap between autonomous and truly autonomous is actually context engineering. Now, for some people, this might be a scary term. For some people, it might be such a familiar term that it's actually trivial. And usually what people think of when they think of context engineering is retrieval augmented generation. And that's basically just giving your LM long-term memory through something usually called semantic search, which usually uses a vector database. Sometimes they'll use a graph database for relations. The problem with this is that this is also not enough. Now, maybe I just have very high standards, but I would like LMs to be able to produce high-quality working code without LM drift, and can include all these things, but this is not enough. Claude Code and open code has shown us through something called agent harnesses that context engineering can be much more complex and intelligent than just RAG. It's not just about enabling long-term memory for your AI agents, because that comes with its own problems. You have a limited context window, but also semantic search is not perfect. So you can pull in memories. How does the LM even know what memories to pull in? It needs the context of what memories to pull in to begin with, right? It needs the intelligence. So while Claude Code, Open Code, Codex, and Ralph Wiggum has shown us the way, they're still not enough. And maybe my standards are a little bit too high, but if we truly want autonomous systems that can do things on their own and produce high quality working code, we need a new set of intelligent systems. Intelligent systems. And these systems will be based around context engineering, like we discussed earlier. What would be in such a system? Let's explore that. Such a system would contain multi-agent systems. And that's a system that can use multiple agents to accomplish a task. This is the key to true autonomy, because imagine a software development lifecycle where a product manager agent takes your feature request, defines it, decomposes it into multiple tasks, gives it to parallel engineer agents that code all the tasks for you in real time, in parallel, and then passes it off to a quality assurance agent that validates the code quality and that the application works, runs tests, and does automated testing, such as automated browser use, where it clicks the buttons in an app that has a user interface and makes sure that everything works. And then the QA agent would mark the tasks as ready for human review before it's deployed into production and automatically pushes it up to GitHub for you. Next would be spec coding. And spec coding would basically be detailed planning sessions with an AI agent and a Kanban board that decomposes your tasks into smaller tasks, each with their own context window and scope, so the LM does not experience context loss, like once again we discussed earlier. The other thing would be validation layers. Now, what a validation layer is in this case, it would be something called a behavior tree. And what it does is it validates the structured output of the LM and can branch based on that output. And the LM will not hallucinate because being probabilistic, right? Unlike in the graceful degradation example, where LMs are left to their own devices, it will not just lie to you. If you do not get the correct answer for the behavior tree nodes, it will reach a explicit and tell you that it couldn't do it and why, which is much better than LMs hallucinating and lying, because then you just have to add a set of nodes with the right set of information to correct it. The final thing you need is a directed acyclic graph. And what a DAG is, sounds very fancy and academic, but really what it is just a graph that flows in one direction, right? So a directed acyclic graph in this case is a graph that defines the flow of a task and the dependencies between the tasks. And that's what allows us to correctly organize tasks and be able to execute them in parallel. But I got great news for you guys. You don't have to implement all these crazy complex solutions. There's already a solution out there that implements all these things that allows you to use your existing Claude Code or Codex subscriptions, as well as any other provider, and take advantage of all of these intelligent, robust systems that, unlike just Claude Code and Ralph Wiggum, allow you to have a truly autonomous system that writes high-quality, robust working code with very little human intervention. And that solution is called AgentLoop. Let me show you guys very quickly. Welcome to AgentLoop. Now, today we won't be discussing every single feature that AgentLoop has because it has many features, but let's just go over some of the features discussed earlier, such as multi-agent systems, spec coding, validation layers, and the DAG. Now, what you'll notice right away is that AgentLoop looks very familiar to those who are familiar with Claude Code or the Open Code interface. GUI with a GUI coming soon. You can switch between build and plan mode. You can open your models command to use your existing subscription so that you don't have to pay an additional subscription for credits. And everything looks somewhat familiar, right? But let me show you what differentiates AgentLoop from just another Claude Code clone or another Open Code clone, and why it's something that's truly special. Now, we discussed spec coding and multi-agent systems earlier. And to visualize that process, we've created a Kanban board in the app, which is controlled by the AI. Yeah, look at that, right? Pretty cool. So these are tasks which were generated by the product manager agent. And this was for, in this particular case, a simple to-do app. You can use keyboard controls to look through the tasks, their description, their execution logs, and have a bunch of observables. You can even use mouse control to hit the breadcrumbs, select tasks, all pretty cool. This allows AgentLoop to decompose a feature request into focus tasks that are moved across the Kanban board automatically by the orchestrator. The orchestrator assigns tasks to specialized agents that can handle the task, run them in parallel, and produce high-quality code output at the end, which will then, once it's in the done column, be ready for human review in a GitHub pull request before it's deployed to production. So this covers multi-agent systems and spec coding. Let's look at the view for directed acyclic graph. So the directed acyclic graph view allows you to see the flow in which tasks are ordered. It also shows you which tasks can be done in parallel. And this allows for intelligent management of dependencies between tasks and knowing what task has to be completed before another task, which allows you to decide which task can be done in parallel based on its previous dependency. For a system like this, you need a lot of observability. So we've also added a status feed. This is similar to something like HTOP or Activity Monitor in Mac OS X or Task Manager on Windows. It allows you to see a high-level view of all of your agents and the tasks assigned to them and what state they're in. And then you can open a view for more information similar to the Kanban board. All right, well, that's all great, but let's see AgentLoop in action. So first, we'll ask it to create us a grocery app. So right now we're talking to the orchestrator agent, and the orchestrator agent is responsible for communicating with all the other agents to accomplish their tasks. And it's a high-level orchestrator that allows for the orchestration and organization of agents so that they can execute their tasks. The way it does this is reads a user's feature request in chat, passes it off to the product manager agent, and it calls a bunch of tools to create tasks on the Kanban board, decomposes it into small tasks that allow you to create your application autonomously without your intervention being necessary in every step of the way. You can see right here that it's creating task dependencies on the directed acyclic graph, the DAG. This allows work to be done both in parallel by knowing what the previous dependencies are, and when the orchestrator executes all these tasks by assigning them to engineer agents, it's able to flow through the directed acyclic graph to make sure that it gets the proper task ordering, proper amount of parallelism, and is able to achieve the end result. All right, let's look at our tasks on the Kanban board. As you can see, AgentLoop has already created all these tasks on the Kanban board for creating a grocery app. Let's take a look at the DAG. As you can see, AgentLoop produced the proper dependencies and proper planning and parallelism for the assignment of tasks on the graph based on their previous dependencies. For example, a user interface can be done in parallel with shopping cart functionality because this is the back end and this is the front end, and therefore they can be done in parallel. And then ultimately, the final step is testing and quality assurance. Now, visualizations all seem cool, but can AgentLoop actually execute this task? Well, let's find out by running orchestrator run. The orchestrator agent is spawning agents to take on the tasks and write your code, all without your intervention. We take a look at the Kanban board. We see that the project setup and architecture planning task has already been moved to in progress. Because this task is a prerequisite for all the other tasks, it did not pull in another task because of intelligent dependency management through the DAG. You can see though that all these tasks to do are queued up to be done by the agents, even while you're asleep, 24/7, creating a truly autonomous system. You can also take a look at the agent logs to see on a granular level what each agent is actually doing. And we see here the typical Claude Code tool call results that allow you to see the diffs of the exact code it's writing on your system, with built-in sandboxing and Git work trees, so that parallel agents do not overwrite other agents' work. So that's all I'm going to show today, but I hope that gives you an idea of why this is so revolutionary, and what is required to make an actual autonomous system that can run on its own and do things on its own and produce working quality code. Thank you for watching. And if you'd like to try out AgentLoop, you can try it out with a 7-day free trial for free with your own Claude Code subscription, or Codex, or any other subscription for free at agentloop.com. I hope to see you there, and I hope to see you guys in our Discord server. Thank you, and have a great day.